Test 1, 2, 3. Okay, well, this is part 3 of forecasting, and I just wanted to spend a little bit of time going over the most robust technique that we're going to use in this course. So I'm going to share a screen in just a moment. But up to this point, if you've been going through the PowerPoints and you've seen the other videos that I put up, you are familiar with the simpler techniques, the moving averages, weighted moving averages, the arguably more robust technique of exponential smoothing and adjusted exponential smoothing. And this will be the third area that we use, which is, at least for our purposes in this course, going to be the most robust technique that we use. Let me share a screen with you, so bear with me just a second. And again, I'll apologize in advance for my coughing or anything like that. Okay, so the third area is what the texts refer to as linear trend line. And you'll notice the formula is very much akin to what you learned in terms of linear regression. And what we're looking for again is the forecast for that next period of demand. You will recall that in the moving averages, the weighted moving averages, the exponential smoothing, the adjusted exponential smoothing to include an underlying trend, what we did was we took a data set of actually demand data, and then we tried to forecast that next period. And in using some of the different techniques, what we found was, well, use a different technique, you get a different result. Is one more accurate than the other? Well, what we will come to see when we revisit this, hopefully right at the end of the semester, when we start to talk about error and so forth, the most robust technique, because the question always ensues, well, geez, which technique should I use? And of course, I gave you a simpler answer early on by saying, well, if you're going into a meeting, quick arithmetic, moving average, and then we can progress to more robust techniques. Well, the other way to answer that question is to say the technique you ought to use, the technique that is most robust, arguably, is the technique that gives you the smallest cumulative error. I usually try and work in error into the semester, but I don't tie it onto the back end of forecasting where it would seem to normally adhere itself, because we have some other things to cover. So I want to cover the three major areas that will be reflected in Betty's BATS. And if and when we have time toward the end of the semester, we'll come back and revisit error. Having said that, trying to forecast that next period. So Y is the forecast for the demand for that next period. We get Y by taking alpha plus beta times X. Alpha is the, hold on one second. Yes. I need 20 minutes. All right, I'll call you when I'm done. Two ways you can always make the phone ring. One, get onto one of these things, and the other is hit the men's room. Guaranteed the phone will ring. So forecasting that next period, Y. Alpha plus beta times X. Alpha is the intercept of a line. We remember that, again, spoke to it the other session about, we have a vertical and a horizontal axis, XY axis. And so where, our projection intersects with our vertical axis, that is the intercept of a line. We remember that. That's alpha. Beta is the slope of the line. And I suppose a lot of ways to look at it, but if you wanted to just stare outside and look at the side of a building or the roof line of a building, it's the idea of rise over run. And so that's kind of what we're doing here. And so when we start to look at, and let me see if I can get the slides to move, we noticed that we needed to define something called alpha, because Y we said was, the demand outcome that we're looking for, the forecast outcome. So we said we needed an alpha, we needed a beta, and we had to understand what X is. Well, the formula for arriving at beta, and we'll do that one first because we need that result to plug in to our calculus to determine alpha. So beta is the sum of the xy's minus n x bar y bar. That's the numerator. The denominator is the sum of the x squareds minus n x bar squared. Okay, well, that makes sense. We already know how to come up with this x bar and y bar. Now think back. In statistics, you learned that x bar was basically expected x. Y bar was basically expected y. How do we get that? Well, we get that with an averaging technique. Almost sounds like moving average, doesn't it? So our averaging technique, which is illustrated here, x bar equals the sum of the x's divided by n, which is the number of the elements that we're talking about. So in the case of a 3-period moving average, expected x in effect was the sum of the 3 x's divided by the number, sum divided by number. There's no mystery there. Same thing with y. Y bar, or expected y, is the sum of the y's divided by n. X bar, y bar. So now we know how to get that part. N. How many inputs? How many elements? 3-period moving average, 3. 5-period moving average, 5. In some of the longer data lists that we had, well, it could be 10, it could be 12, trying to forecast that 13th period, or whatever. So n is the number of elements. So we got that part. That's easy. Then the numerator says the sum of the xy's. Well, we're going to see in a minute how we get xy. And once we do that, then we're left with the denominator, which is the sum of the x squareds. Don't have any x squareds yet. Minus n, which we just discussed, so we know what n is. Then it says x bar squared. So if we can calculate x bar, any number times itself, is squared. So we know how to get x bar, so all we have to do is square it, and we have that. Okay. So let's take our example where we're trying to forecast the 13th period. Now remember the formula, keep that in mind, sum of the xy's and x bar, y bar, sum of the x squareds. Okay. So our period, we're going to assign the variable x, and one of the things we need is the sum of the x's. We sum x, in other words, add, total 78. So the sum, this big capital sigma here, sum of the x's is 78. We're going to assign the demand numbers, the actual demand data, variable y. Sum of the y's. Add the numbers, 557. Now, we remember from the formula up here, that we need sum of the xy's. Sum of the xy's. How do I get an xy? This is tough. X times y. 1 times 37, 37. 2 times 40, 80. 3 times 41, 123, and so forth. And pretty soon we find we've got an entire column of xy's. Well, what did we need in the numerator? we needed the sum of the xy's. So now we have xy's, sum the xy's, and we have 3867, 3,867. Other thing that we needed was in the denominator, the sum of the x squareds. Well, how do we get x squared? X times itself. 1 times 1 is 1. 2 times 2 is 4. 3 times 3, 9. 4 times 4, 16, and so forth. And here again, the sum of this column of x squareds is 650. So we now have a bunch of information. So x bar, which there's a bar, but it looks like it moved in the slide. I'll have to fix these. So this is actually x bar. So as you're making notes to yourself, this is not x, this is x bar, expected x. How did we get that? Well, remember, sum of the x's divided by n, or the number. Sum of the x's is 78. How many elements are there? 12. 78 divided by 12. So x bar, expected x, is 6.5. Same thing here. Y bar. I know it looks like Y, but there's actually a bar that seems to have shifted over there. But anyway, Y bar is the sum of the y's, which is 557, divided by n, the number, which is 12. Y bar equals 46.42. Expected x is 6.5, expected y is 46.42. So looking back at our formula, beta is arrived at by the sum of the xy's, and we had that number, in this column right there, sum of the xy's. Sum of the xy's minus n, which we know is 12, x bar, which we just calculated to be 6.5, y bar, which we just calculated to be 46.42. That's our numerator. All of that divided by the sum of the x squareds. Sum of the x squareds is 650 minus n, which we already know is 12, x bar squared, x bar 6.5, and then square it. Once again, the words of Robert De Niro, do the math, beta equals 1.72. So that's our slope of the line, 1.72. Now to get alpha, remember when we looked at that over here, alpha, y bar minus beta times x bar. So again here, alpha, and you see the bars have shifted over. Again, got to fix the slide. So y bar minus beta times x bar. Well, we already calculated y bar, 46.42. We've already calculated x bar, 6.5, and we just got done calculating beta, which is 1.72. So fill in the blanks, 46.42 minus 1.72 times 6.5, and we end up with an alpha, or intercept, of 35.2. So again, remember our formula, y equals alpha plus beta times x. Alpha, we just calculated, 35.2, plus beta, we just calculated, 1.72 times x. Uh-oh, what's x? It's the next period. Well, how many periods do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the next period would be what? Exactly, 13. So when we look at this, y equals 35.2 plus 1.72 times 13. In other words, our forecast using, and this is kind of a ordinary least squares example. So using all the data we've just assembled, using linear trend line, linear regression, y equals 57.56. And it's taking the actual data and giving us a linear, as opposed to curvilinear, et cetera, but a linear projection. You'll see alpha, intercept, and then of course the slope of the line. So that's our linear trend line. Now, we'll come back to talking about seasonal adjustments. We're not going to do that because we don't need it for Betty's bats. So we're not going to do it right now, but we spoke about it earlier and we have those slides here. So I encourage you to look these over. We're not going to discuss them today. We will come back later in the semester, even though it's an abbreviated summer session, and we'll talk about that. We do want to mention a couple of things about forecast accuracy in terms of error and so forth. And again, we'll revisit this at the end of the semester, but error, when we're speaking in terms of forecasting error, we're talking about the actual data number versus what we had forecast in anticipation of that result. Net those out and you have your error. Well, again, what are we after? Well, ultimately, we'd like to choose the most robust technique that minimizes error or gives us, in effect, the smallest cumulative error. We also can express this in terms of mean. Mean means average, we know that. Mean absolute deviation, or in terms of a percentage of this mean absolute deviation, and then subsequently cumulative error. So just for having said it once, and we will revisit this again, but mean absolute deviation is the sum of the, what do these vertical lines mean, as opposed to parentheses? That's right, absolute value. In other words, we don't care about the polarity. The sum of the D minus Fs. In other words, the sum of the actual demand versus what we had forecast, that error. So the sum of the absolute value of D minus Fs, and you can't see it well, but faintly you can see the line. So that's the numerator. The denominator again is N. So that if we looked at this, 12 periods of data, this is the demand data using, remember, exponential smoothing with an alpha of 30%. Okay, so we used this number, the demand number, twice. We talked about Y. So these are the forecasts that we made. And you can see they're different. When we look at it, and if we were to, now of course the first one, since it's demand data, use twice, we expressed that already. So we don't have an entry there, which leaves us, by the way, 11 elements. But again, another discussion. We look at the error. So the demand was 40. That's what actually happened in February. We had forecast 37. How wrong were we? 3. We were off by 3. 41 in March. We forecast 37.9. How wrong were we? The difference, 3.1. Okay. April, we forecast 37, or the actual demand number was 37. We forecast 38.83. Again, how wrong were we? Well, on the other side of the number line, remember the number line, 0, positive, negative, okay? So we were wrong on the other side of the number line by 1.83. And you see this all the way down. Now we can take a cumulative number because that's what we're tasked to do. Take a cumulative number. And when we add these or sum these, we end up with 49.31. Well, is that actually a legitimate reflected amount? Well, the problem is what? We are going to understate our cumulative error. Why? Because simply adding these numbers, we're adding the negatives, which is why the formula calls for the absolute value, because we eliminate the polarity. And so when we accumulate this column of errors, this is because does it really matter? I mean, sometimes it does. But in our example, does it really matter whether we were off to this side or that side of the number line? Not really. It's just the accumulation of these errors between our forecast, our guess, and what actually transpired. So looking at it that way, this is more accurate in terms of our cumulative error. And so if we were to try and calculate mean absolute deviation, the sum of the absolute value of the D minus Fs, that's this 53.39, divided by, so our denominator, as I mentioned, we had nothing in the first slot here. So our N is actually 11, not 12. So we end up with a mean absolute deviation of 4.85. And we can then go on to, percentage, mean absolute percentage deviation, cumulative error, average error, and so forth. But, this is kind of what we're looking at. You see the error, exponential smoothing, where we weight demand data 30%, forecast data 70%. This was our cumulative error. Exponential smoothing using 50, we equally weight demand and forecast data, bit smaller error. Adjusted exponentially smooth data, adding the underlying trend, even smaller. And then looking at it in terms of percent, look what gives us the smallest mean absolute percent deviation, of the techniques we're using. Linear trend line. Ergo, therefore, our most robust technique is linear trend line. All right, so then we'll talk more about out of control forecasts and tracking signal at the end of the semester. But basically, it's if we were to pick, and we remember this with fondness from statistics, remember small sigma, remember standard deviation, 99.97, depending on which textbook, 99.99 percent of all of our error falls within plus or minus 3 sigma, 3 standard deviations. Well, again, we'll be revisiting that, and we start to talk about what is a good result, a good part, a good donut, a good hamburger, a good scheduling, situation with CAT scans, whatever it might be. We set in essence, between 0 and 3 positive and negative standard deviations. And once we identify what that standard deviation is, then we can measure, in a sense, what's good, what's bad, what exceeds certain limits that we may have set. And maybe the limits are in terms of a service, the time it takes to do a CAT scan. Well, it's okay if it's between 5 minutes and 7 minutes, but if it's 8 minutes, it's too much, whatever it happens to be. But we can then start to look at error in a meaningful way. And again, if we look at statistical control charts as we were, small sigma equals, and again, you have to look closely, but it is the square root of the sum of the D minus F squared. That's not absolute value, those are parentheses. So the sum of the D minus F squared divided by N minus 1. And we remember from statistics, not N, but N minus 1, because that's right. It's a sample, not a population. Anyway, so, we'll be revisiting this at the end of the, semester, presuming we have time. And then once we play a little bit more with this, linear regression, same formula, we will revisit this and, play with some other numbers, wins, losses is one of the textbook examples and so forth. And we end up with our regression line. And once we do that, we can look for correlation, and then this R squared, or coefficient of determination, as it's in a sense explanatory power of what we're looking at and so forth. and we will talk about computing correlation, which is here, and ultimately computing R squared, and this coefficient of determination, is something highly positively correlated, an inverse correlation, highly negatively correlated, and so forth. So, we get a chance, we'll talk about that. We will not be discussing multiple regression. So anyway, I'm going to stop share. Um, these are the 3 areas that will be on that first quiz. So you have the PowerPoints, you have my rhetoric. Hopefully it's a bit helpful in looking at this stuff. I am tasking you, as in the previous techniques, to go and try this. I mean, you can have the laptop do it all for you. That's fine, but it would be something that would be, I believe, a positive tool for you if you can go ahead and do that. So again, we will likely at the end of this week, per the syllabus, send out a quiz, our first quiz on forecasting, and it will cover each of the 3 areas. It's going to have moving average, it's going to have weighted moving average, it's going to have exponential smoothing. I don't recall whether I gave you an example in the quiz of adjusted exponential smoothing. I don't think so, but it will also have linear regression. So if you can look these things over, if you can play with it a little bit, and so forth, you should be golden. And it is a take-home quiz. So if I give it to you, for example, this Friday after our voluntary Zoom session, if I post it then or Saturday or something, then roughly speaking, it'll be due Monday or Tuesday or sometime next week. I'm not going to give you an artificial due date, because I promise you I'm not going to be going over the results of that on Monday or Tuesday of next week. So anyway, that's about it. Email me if there are concerns. Aside from that, enjoy your day. This will conclude our videos on forecasting. From here, we will start to look at Frank's fine floats, and we'll talk more about that in the next session. Have a great day, great weekend, and again, play with this the rest of this week, and hope to by Friday post the quiz for you. Enjoy your day. Chat soon.